One of the things that we talked about when we first started talking about the kinetic molecular theory is number one, that the molecules don't take up any space in the container, and then number two is that they're not attracted to each other. Okay, going back to that first one though, where the molecules or the gas particles don't take up any space in the container, basically means that if you have a mixture of gases in a container, for example, you've got some oxygen, some nitrogen, and some fluorine gas all in a container together, and you want just the pressure of the oxygen or the nitrogen or whatever, you can act as if the other gases aren't even there. And so when you have a mixture of multiple gases, you can find the total pressure of the gases. So the P total here is the total pressure by taking the individual pressures of each of the gases and adding them together. Because again, remember that we act like the gases don't take up any space, and so when a gas is in there with other gases, when we're talking about just the oxygen, we don't even consider the other gases. Okay, so in this case, if the pressure of gas C, whatever that happens to be, that is what when we refer to the partial pressure. That's a little bit kind of a weird way to say it, because the total pressure is all of the gases added together. But if you're just talking about the pressure of, let's say, gas C, let's say that's oxygen, well, we refer to that as the partial pressure. So many times they'll say the partial pressure of O2 is, and you're like, well, wait a minute, what? I want the whole pressure of oxygen, not the partial pressure. When they say partial pressure, they're referring to it's part of the total pressure. So when they say the partial pressure of O2, they just mean what's the pressure of just the O2 part, not the pressure of the whole thing. Okay, so don't let the word partial pressure mess you up. Partial pressure just means the pressure of that individual gas, not the total pressure of all of the gases put together. Okay, and so likewise we can use that same thought we can use the total pressure by using the total number of moles. So just like with pressures, the N total, the total number of moles, is equal to the moles of gas A plus the moles of gas B plus ... You can just add up all of the moles of the gases to get the total number of moles. Okay, and then you can use that as well to find what's called the mole fraction. Now on the AP test, they do give you this equation that looks I'm looking at the equation here, and it looks exactly like what this one is, but they don't call it the mole fraction. They just say if you want to find the pressure of a gas, not the total pressure, but let's say you want the pressure of just the oxygen within this mixture, then you take the total pressure and you multiply it by this. And they don't call that anything, but that right there, that X of A, is the mole fraction, because then they do tell you afterwards what the equation is. You just take the moles of A and you divide by the total moles. But at no point do they ever refer to it as the mole fraction. Okay, now the mole fraction is a little bit misleading because the mole fraction is written as a decimal. So even though you write it as a fraction, you still get an answer that's going to be in decimal form. Not a percent, just a 0.52 or a 0.41, something like that. Okay, so let's look at an example of this. Let's say you've got 7 moles of nitrogen, 2.5 moles of oxygen, half a mole of helium, and the total pressure is 0.90 atmospheres. And then they want to know, what is the partial pressure of the nitrogen? Okay, that means what is the pressure in the container just due to the nitrogen? So to find the pressure of the nitrogen, we're going to take the total pressure, 0.90 atm, and we're going to multiply by the mole fraction of nitrogen. So how many moles of nitrogen do we have? 7. And what is our total number of moles of gas? 7 plus 2.5 plus 0.5 is 10. So 7 divided by 10, and you could certainly use a calculator for this. 7 divided by 10 is 0.7. 0.7 times 0.9 is the same as 9 times 7, which is 63. So it becomes 0.63 atmospheres. Okay, and so that's a good use of learning how to do mole fraction, learning how to use this equation to find the pressure of an individual gas. Okay, and obviously if we wanted to find the pressure due to oxygen, instead of 7 right here, we would just write the moles of oxygen. We just put 2.5. And if they wanted helium, we'd put the 0.5 there. Okay, Now, when does this get used? It gets used a lot when you're collecting a gas over water. Okay, for example, when you're using a gas collecting tube, and a gas collecting tube is something you hold, it's inverted, it's usually about 100 milliliters. Okay, and so basically you fill all of this up with water. So you've got a bunch of water in there. And if you're in my class last year, we might have done this with the cigarette lighter, the butane lighter, where you hold the lighter underneath here and you let the gas bubbles come up. And what happens is slowly as you let the bubbles come up, what does the water do? The water slowly starts to go down. And then this top part up here gets filled with gas. Okay? So you've got a spot, eventually you're going to put a whole bunch of gas in there. So let's say your water level's way down here, okay? So there's your meniscus. You're reading from the bottom of the meniscus, wherever that's at, and that will tell you how much gas is in there. Okay, now when you do that, yes, this space above this, all of this space up here is filled with gas, but the gas is going to be, yes, some of the butane that you let in there, but remember that water also evaporates to a small extent. So a very small amount, but some of that space up there will be water as well. So the gas displaces the water as you put more gas in there. The water also begins to evaporate though and creates some of the pressure inside the tube. So therefore, this total pressure here is mostly the pressure of that gas, but it's also some water vapor as well. Okay, so let's see how we're going to use that to help us answer a question. Okay, so it says 45.7 milliliters of hydrogen is collected over water in a gas collecting tube from the reaction between magnesium and hydrochloric acid. At 45 degrees Celsius, the pressure is 780. So when they say atmospheric pressure, that's referring to the total pressure, okay? Total pressure. How many moles of hydrogen are in the gas collecting tube? At 45 degrees Celsius, the water vapor pressure is 71.9. So if the total pressure inside that tube is 780 and 71.9 of that is due to water vapor, then whatever's left has to be due to the hydrogen. So the first thing we're going to do is we're going to take the total pressure, 780, and notice they use millimeters of mercury and torr. Remember that those two are the same, so it doesn't really matter. You don't have to convert to one or the other. So 780 minus 71.9 gets us to 780 minus 71.9 gets us to 708.1. So again, what that means is it means that of the total pressure inside that container, 708.1 millimeters of mercury are due to the hydrogen. And again, about 10% of that is due to the water vapor pressure of the water H2O gas. Okay? And anytime you collect a gas over water, you have to consider the water vapor pressure. And knowing that the total pressure inside that container is due to the water and whatever gas you're putting in there. Okay? So that's a very, very common use of what's called Dalton's partial pressures, is that, again, the total pressure is due to the individual particles of the different gases that are in there. Okay, now we're almost done here. They want to know moles of hydrogen. So we've got the volume of hydrogen, so we're going to use PV equals nRT, and they want moles, so moles is going to equal N equals PV over RT. So the pressure is, and watch how I do this, 708.1. I need it in atmospheres though, so I'm just going to divide by 760 right there in the problem. The volume is in milliliters. I need it in liters, so 0.0457. And yes, I'm being lazy and I'm leaving out units. I know, I'm a terrible person. Okay, the R, 0.08206. And then the temperature is 45 degrees Celsius. 45 plus 273, I believe, is 318 Kelvin. Okay. So I'm going to take 708.1, divide by 760. Don't care what the answer is, but there it is on my calculator screen. I'm going to multiply that by 0.0457, divide by 0.08206, and then divide by 318. So I'm not sure if you can see it on my calculator screen, but when I do this all in one step, remember, if it's on the bottom, I divide here and I divide here as well. Okay, and or you've got to put the whole thing in parentheses. Anyway, so I get a final answer of 1.63. That's a 1, sorry. 1.63 times 10 to the minus third moles, or just 0.00163. Okay? And that is the correct response, I hope. Okay, example 3. Here's one from a recent AP exam. So here, again, anytime they use letters like that, that's just a made-up fake element, then they don't have to worry about is it the right chemistry or not. So it says, as shown in the following diagram, 10 milliliter samples of HBr of various concentrations are added to sample E in a closed test tube. So this here is our gas collecting tube right here. At the start of each trial, the gas collecting tube is completely filled with water. Okay, so we know that the water is going to start to go down like we just talked about. The samples of E react with HBr, and the H2 collected is collected in the gas collecting tube. Okay. The enlarged view of the gas collecting tube at the end of trial 3 is shown in the diagram above. What should the student record as the volume in milliliters of H2 collected in trial 3? So here's where you, and I think we've talked about this already, but remember, you have to go out one space where you're guessing, where you're not sure. Okay, so to me, this is definitely between 42 and 43, no question there. So I'm going to say 42 point. Now I'm going to start counting down. 42.1, 42.2, 42.3, 42.4. It's definitely 42.4 something. Now, the next number I don't know. These ones I do absolutely know, but the next one I don't. So what that means is now's the time where I have to guess. Now, this is the part where they don't care, but they do require you to go one more. Is it 42.45? Is it 42.46? Again, it doesn't matter. You just have to put another number. What if that line was right on? What if that curve came all the way down to here and it was right on this line right here? Okay, well then you would say 42.50. Okay, because the 42.5 is sure, and then I think it's 42.50. So to me, we're right in between 42.4 and 42.5, which means I'm going to say 42.45. That's my unsure. You always have to put one unsure digit in there, okay, based on the accuracy of that measuring tool. Okay, now I'm sure. Now I haven't looked at the answer sheet, but I'm sure that they accepted any answer between probably 42.42 and 42.49. Okay, anything in there they would have accepted. But I kind of either go right into the middle, 42.45, or if it's close to the next one, if it was really close to this or really close to this, I would say 42.50 or 42.40. If you go halfway or all the way, then you're always going to be fine. In this case, it's clearly not on 42.4. It's clearly not on 42.5. So 42.45 is a very, very good answer. And again, that's the key. If you put 42.4, they're going to mark it wrong. Okay, part B. In the laboratory, the temperature is 294 Kelvin. The pressure is 754.7. Vapor pressure of water is 18.6. What's the pressure? So pressure using PV equals nRT. P equals nRT over V. Okay, let's see. So the moles, let's see, do they tell us the moles? You start with a 10 milliliter sample of HBr. You've got the volume of the hydrogen gas. Oh, I'm sorry, I'm thinking way too much into this, aren't I? Is this the last question? It is, wow. So, way too much into this. Let's go ahead and back up here. If they just want the pressure, determine the pressure of the H2. Well, again, the total pressure is 754.7. And then the water vapor pressure is 18.6. That's all we've got to do here is 754.7 minus 18.6 equals 736.1 millimeters of mercury. Okay, and yes, you would have to show that. The subtraction there, don't just write 736.1. Now, let's go a little bit farther, though, because that's it for that question. That's all you had to do. Is now, how could you figure out the moles? Okay, and let's see, do we have? I think we have enough. So moles again would be PV over RT. Let's see, the pressure, we just figured it out, is 736.1. Get that into atmospheres though, divide by 760 if it's millimeters of mercury or torr. The volume we did up here, and that's in milliliters, so we need to move that decimal point 3 spaces to the left. So there's our liters. R is 0.08206, and I know they didn't ask to do this, but again, this is if you want to make sure you know how to do these problems. Let's just take it the farthest they can take this, really. So 736.1 divided by 760 times 0.04245 divided by 0.08206. And when I'm saying this out loud, this is exactly how I'm typing it into my calculator. So I'm dividing by 0.08206, and then I'm dividing by 294, no parentheses needed. And again, a pretty small number here, 0.00170 moles of H2. Okay, and that's a good introduction there to partial pressures.